All right, welcome. We're going to go ahead and go through the practice test, and this is going to be pretty directed as far as how the test is going to lay out, because this is a new topic. We're going to be dealing with some vectors. The test begins, as you will see, this is going to be what the first problem on the test is going to be. However, of course, the angle measures and the lengths are going to be different. But you start out with four, either law of sine, or two, excuse me, either law of sines or law of cosine problems. I may create another video and add on to this, but I'm going to work on the assumption that right now you know the law of sines, cosines, you're competent at those. So there is attached at the bottom of the website, this is purpleshirtednerd.com, this is chapter 6 practice test. There is an attachment that would have the key to these problems if you want to practice those. But the first problem on the test might be like this, or it could be a different triangle to solve. You can probably expect you're going to get a law of cosines problem and a law of sines problem, and perhaps one problem of those will have ambiguous case solutions. So there's four example problems before we start getting into some of the material that is new. This should be your third year, I believe, where you've been solving triangles with law of sines and cosines. So there's four problems on the practice test, just two of those on the test. Okay, then we get into some area. These are some specific formulas for finding areas. So if I had three side lengths, there is a formula, Heron's formula, that says the area of a triangle, if we're given three side lengths, this is side, 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 side formula is big square root of s, whatever that is, times s minus a times s minus b times s minus c. S is, and they use s for this because it stands for semi-perimeter, or half the perimeter. So s is 17 plus 22 plus 36 all on 2. So what does that give us? That gives us 39, 75 on 2. So our area would be, and if we're okay entering on calculator, we should be in good shape here. 75 on 2s times 75 on 2 minus 17, s minus a, times 75 on 2 minus b, 22, times 75 on 2 minus c, 36. And now we are just calculator entry and careful entry on a calculator away from our solution. And our solution to that problem should be 133 approximately 0.69 square units. Okay, so this is a formula to know. Your problem on the test can be very, very similar. You'll be given three side lengths. Okay, then you have another formula for SAS problems. And as you can see, if I was to draw this triangle, not trying to draw it to scale, and I had ABC, I have angle B at 58 degrees, and I have side C at 9, side A at 5. We see, oh yeah, this is an SAS triangle. This is an oblique triangle formula, and it's an awful lot like our regular formula for finding the area of a triangle, 1/2 base times height. It starts out that way. Area equals 1/2 times, if it's side angle side, one side times the other side, but then sine of the included angle. That formula is area equals 1/2 times the two sides times the sine of the included angle. You'll need to know that formula. That, if you go ahead and punch it through, of course, better make certain your calculator is in degrees on this, but that answer should be approximately 19.08, and of course that's an area, so square units. Okay, then on the test, you're going to be given a few vectors so we can see what's going on with vector u, v, w, and then you're just asked to recreate, redraw, sketch the new vector that are combinations of u, v, and w beginning at the origin. So 2w, I want to take w. W is a vector that goes right 1 and down 1, and I want to do that twice. So w is the vector that goes right 1, down 1, gets me to here. There's w, but 2 of those gets me to here. That is 2w. Problem 2, I want negative, so backwards, half of v. V is a vector that wants to take us to the left 2 and down 2. Backwards, that would be to the right 2 and up 2, and half of that would be to the right 1 and up 1. So there is negative 1/2 v. Now, v minus w. This is one that people might, I think we know what to do, but you may have a chance of losing some points on this if you're not careful with this. We want to apply vector v. Vector v wants to take things, as we can see again, left 2, down 2. So vector v starts here and wants to take us to there. And then we want to subtract w. W wants to, if we were adding w, we would be going right 1, down 1. So to subtract it, we're going to do the opposite. We're going to go up 1, left 1. And that gets us to here. This is kind of like v, this is minus w attached to that. But the vector we end up with is what we want to really show. This is the vector we end up with. That is v minus w. Likewise, number 4, u. U is a vector that wants to go to the right 1 and up 2. So I'm going to start with u. Right 1, up 2 would get me to here. And then I want 2 w's. And each of those w's is going to take me to the right 1, down 1. So to the right 1, down 1 gets me here. That's a w. And there's another w, and I end up right here. But the vector u plus 2w is what I'm really interested in. That is this guy. The rest of this is really scratch work for me to come up with my solution. Okay. All right, pretty mechanical, hopefully pretty simple for you, something we can get done really quickly, especially since we know it's coming. Test's going to be very, very similar to that. I may either change the vectors u, v, w, or perhaps I'll just change those. Find the component form and the magnitude of a vector with initial point 5/2, -2, and terminal point 1/2. Okay, so I've got a vector that is starting at 5/2. Its x component starts at 5/2 and goes to 1. That means this vector has traveled from 5/2 to 1. The distance it has traveled is 1 minus 5/2. Likewise, y has gone from -2 to 2/5. That is 2/5 minus 2. So I end up with -3/2. And let's see, that would be 2/5 minus 10/5. Oh, that's minus -2. I bet you caught that. 2/5 minus -2, 2/5 plus 2, 2/5 plus 10/5, 12/5. So in order to get from this point to this point, I've had to go to the left 3/2 and up 12/5. That is the component form of the vector. We still need to find the magnitude. If you're watching this, I certainly hope you do not forget to find the magnitude as well. But the magnitude of a vector is just the hypotenuse. In other words, here we have a vector that wants to go, let me redo that. Here we have a vector that wants to take us left and up. This may not be to scale, but something along the line of this. Therefore, we've gone left 3/2, we've gone up 12/5. The magnitude is the hypotenuse. So this is just Pythagorean. So our magnitude we get by taking -3/2 squared plus 12/5 squared, and we take the square root of that. So we end up with 9/4 plus 144/25 square root of this guy. And when all is said and done, and we go through the simplifying of that, we should end up with our magnitude of our vector. Let's call it v, perhaps. Magnitude of v is 3 root 89 on 10 if we're looking for the exact value. Find the vector v with a magnitude of 10 in the direction of vector u. So here's vector u. Vector u wants to go to the right and down. Vector u looks like this, 1 negative root 3. We want a vector to go in the same direction but end up with magnitude 10. Now, I'm gonna avoid a trap on this. If you say, well, this is a 1 negative root 3, this is a 2, this is a 60-degree angle. You may shortcut this and that may end up hurting you. So what if we don't give you a nice 30, 60, 90 or 45, 45 triangle? How could we approach this? If I called this x and this y, these triangles, if they're going in the same direction, are similar. And therefore, I can say x is to 1 as 10 is to 2, so x is 5. And I can say y is to negative root 3 as 10 is to 2, so y is negative 5 root 3. So there we have it. Yes, we could have said, oh, this is special. This is 60 degrees, making this 60 degrees, making the short side 5 and the middle side 5 root 3, but it's down for negative. But if the angle was not so nice, we better approach this from similar triangles. Sides are proportional. Okay, find the component vector, the component form of the vector with a magnitude 4 root 3 and a direction angle of 120 degrees. So we've got a situation something like this. 120 degrees gets me to right here. I've got a magnitude 4 root 3. That creates a 60-degree angle in here, and now I've got a 30, 60, 90 triangle. If I didn't have a 30, 60 or a 45, 45, I could SOHCAHTOA this. If this went 123 degrees and I had a 57-degree reference angle, I could find my missing sides of this with SOHCAHTOA. But because it's 30, 60, 90, I'm going to take advantage of that. This side is half the hypotenuse, 2 root 3. It's negative because it's to the left. And this side is square root of 3 times the short side, negative 2 root 3 times root 3, negative 6. So our component form is, oops, this is positive 6, sorry, positive 6 is negative 2 root 3 and up positive 6. Pretty simple. This is just a disguised problem that we were doing weeks ago. In fact, this is a disguised problem that you should have been comfortable with a year ago. Find the angle theta between two vectors. This is a really, really slick formula. If we have two vectors, u and v, then the angle between them, cosine of that angle, I'm going to call it, well, they have called it theta. Cosine of theta should equal u dot v over magnitude u, magnitude v. What a great, this is a huge time saver compared to if we were going to do this geometrically with a combination of algebra in there. This is really, really slick. So theta then is equal to cosine inverse of u, 2 negative 3, dot v, 1 negative 2, over their magnitudes. Well, the magnitudes, understand, this is our x component, our y component. We're just looking for the hypotenuse that works with legs of 2 and negative 3. So the magnitude is x squared, that's 2 squared 4, plus y squared, negative 3 squared 9, square root of, times magnitude of this guy, 1 squared, 1, plus negative 2 squared 4, square root of. So we end up with cosine inverse. Let's apply our dot product in the top. I get 2 plus 6 over root 13 times root 5, or cosine inverse. The exact answer is cosine inverse of 8 on square root 65. That's our exact answer. If we take that guy to calculator for this problem, let me check real quickly here. If we take that to calculator, find the angle between, we get 7.125 degrees approximately, depending on how you're to round that, perhaps 7.1 degrees. Really slick way to find angle between two lines, or in this case, two vectors. Okay, find the values of k so that these vectors are orthogonal. Orthogonal is the vector land equivalence of the mathematics land perpendicular. Now, as it turns out, there's a couple ways. We could go to math land and handle this, but in vector land, there's a rule that says they are orthogonal if u dot v equals 0. So if I take negative 3k comma 5 and dot product that with 2 negative 4 and set that guy equal to 0, I get 0 equals dot product negative 6k plus negative 20, or 6k equals negative 20. K is negative 26 or negative 10/3. Okay. We could also say, it's probably worth noting that the slope, we'll call this slope 1, the slope 1 is 5 on negative 3k. Why is that? Because this vector is changing, is going up 5 as it's moving negative 3 across the x-axis. Likewise, slope 2 is equal to negative 4 on 2, or negative 2. And then if we wanted those to be perpendicular, we could do the whole opposite reciprocal and set up a new equation. I'll leave that to the viewer. Dot product in this case, if we're given vectors, we may just want to stay in vector land. Okay, pretty straightforward here. Maybe the biggest challenge on this might be you just write down the right vectors. So here we want vector v, so I'm going to write that one down. Negative 3, 4. Dot vector w, 1, negative 4. These should be very, very quick. Dot product, negative 3 times 1 plus 4 times negative 4 gives us negative 19. 4 times, I'm going to make sure to write down the correct vector, 2, 2, because there's no reason I should miss these. Then we will dot that against w, 1, negative 4. So I end up with 4, the scalar, times vector 2, 2, the vector that's 2, 2, and I get 8, 8, which I still need to dot with 1, negative 4, careful, vector, equals 8 times 1, 8, plus 8 times negative 4, negative 32, and I get negative 24. And finally, just a big old combination of things here. I'm going to write everything down correctly. U is 2, 2 times 2 times W, or dot, 2 times W. I'm going to go ahead and do that right here. That's 2, negative 8. And we're supposed to do that dot product and then multiply that, not dot that with V, because by the time we're done dotting this, we're going to get a scalar. So I get 2 times 2, 4, and 2 times negative 8, negative 16, and that's supposed to be multiplied by vector v, negative 3, 4. So that becomes negative 12 times negative 3, 4, or 36, negative 48. Okay, really simple. Those certainly should not be problems we spend time thinking on. We should just be able to snap to it, make sure we get the right vectors written down. Okay, then we got a series of story problems. Two planes leave an airport at the same time. One is flying 425 miles per hour, and it is going primarily north. And another one is going north as well. So I'm going to leave a lot of room up for my diagram. I like big diagrams for these. So one is flying 425 at a bearing north, but 5 degrees to the west. This is a bit more than 5 degrees, but it gives me a little bit of working room here. And it is flying at 425 miles per hour. I'm going to come back to that. The second is flying at 530 north, but rotated 67 degrees to the east. Maybe something like this. And it is flying at 530. Determine the distance between the planes after they've flown 2 hours. Well, after 2 hours at 425, this plane would have traveled 850. 2 hours at 530, this plane would have traveled 1060. And I'm left to find the distance between the planes. I want to find this distance. So what do I know in my triangle? I'm interested in this. I've got an 850. I've got a 1060, but I know this angle is 5 degrees and 67 degrees, 72 degrees. So I have side angle side. I can solve this triangle. I just want to find x. So, law of cosines. X squared is 850 squared plus 1060 squared minus 2 times 850 times 1060 times cosine of 72 degrees. Or x is big square root of all of that, and we're ready with careful entry in calculator to arrive at our answer. And our answer on this, after you plug that in calculator, ought to be approximately 1,135.45. In this case, our unit measure is miles per hour, so miles. Pretty straightforward. Shouldn't have to spend a whole lot of time thinking. Just throw together your diagram carefully and have at it. All right, this is a problem that we've kind of specialized in this chapter, and that is the classic tension problem. Two cranes are holding up 12,500-pound beam in place while workers weld it into place. The cable of one makes a 32.8 degree angle with the horizontal. So maybe something like this. So here's our crane coming off there, holding this guy up. And the other 44 degree angle with the horizontal. So maybe something like this, 44.2, sorry. Get that? Yep. 44.2. Now, we have a 12,500 pound weight being held in place. And I'm going to break this into components. This crane is holding this with a force directed this way. The crane on the right, force directed that way. There's our crane. And I'm going to call this tension 1 and this tension 2. Now, there are different things going on here. One, that the cranes are supporting 12,500 pounds, but they're also fighting against each other. One of them's pulling, some of its effort is being pulled to the left, some to the right, but those left and right components are balancing each other out. In other words, the force applied this way is equal to the force applied that way. Otherwise, this 12,500 pounds would be moving right or left. So I'm going to talk about that force. I'm going to call this X1 and this X2. If I just fill in a triangle here, and I take a look at 32.8 degrees on the left, I notice I'm interested in the adjacent. I've also mentioned the hypotenuse, so I can say cosine of 32.8 degrees equals adjacent my x1 on my t1. And therefore, x1 could be called t1 cosine 32.8 degrees. And likewise, I could talk about x2 over here, and x2 is going to end up, by the same discussion, is going to end up being cosine of 44.2 degrees times t2. What do I know about those forces? I know those forces are equal, and I could say t1 cosine 32.8 equals t2 cosine 44.2, but I could also write it this way. t1 cosine 32.8 degrees minus t2 cosine 44.2 degrees should equal 0. Okay, let's talk about the vertical components here. The vertical components, if I call this y1 and this y2, those are not necessarily equal. In fact, I think it's a pretty easy argument that y2 should be bigger than y1. y2 is doing more of the upward lifting, less of the fighting. So it's doing more of the upward lifting. What I do know about y1 and y2 is they are counterbalancing the downward force, the 12,500. Okay, I will jump over here and just talk about y2 on the right for just a moment. From 44.2, y2 is the opposite, and I want to talk about t2, so I'm going to say sine of 44.2 degrees equals opposite y2 on hypotenuse t2. So y2 is equal to t2 times sine 44.2. A lot of 2's there. By the same discussion, y1 should be equal to t1 times sine of its angle, 32.8. But those guys are working together against the 12,500 pounds. So t1 times sine of 32.8 plus t2 times sine of 44.2 equals 12,500. They're balancing those. And what I have here is a system of equations. And to solve that system of equations, we're going to go ahead and use some technology. We're going to go into our TI-83s, 86s, whatever TI instrument you're using. We're going to create a 3x3 matrix. So we're going to go into matrix, edit the matrix, and we're going to put in cosine of 32.8. And we're going to put in a minus cosine 44.2. Whoops, cosine, sorry. Try that again. Cosine 44.2. And we're going to put in a 0 in our 3x2 matrix. And then we're going to go ahead and put in sine of 32.8. And if you're set in degrees, you can just enter sine of 32.8 and it'll put it as decimal equivalent. Then I'm going to put in, this is plus, so plain old sine of 44.2. And then I'm going to put in a 12,500. And once that matrix is entered, we should be able to go to our matrix math options and scroll down until we get to RREF, row reduced echelon form. Type that in, and on our calculator it's going to say RREF, and then it's going to say what matrix do you want to put in there. We go back, we select the matrix, perhaps A, hit enter, and that will give us our results for T1 and T2. And as it turns out, our T1 value, running out of room here, our T1 value is 9197.1, and our T2 value is 100783.5 approximately. So those would be pounds of tension on each of those two. And as we said earlier, we did expect T2 to be doing a little bit more of the lifting because it's lifting more. It has a larger Y2 component. So pretty good problem. Very, very classic representation here. It's one that it is honors worthy. However, all I'm doing on this test might change that value, and that value, and the words are going to stay the same. So you should be prepared for that. Okay, and number 3, a force of 45 pounds in the direction of 30 degrees above the horizontal is required to slide a table across the floor. So here is my table. And we are applying a force above the horizontal 30 degrees of 45 degrees here. We are to end up finding work, but work equals force times distance. So not 45 degrees, just 45. So you might say the force is 45, but the force of 45 is not 100% efficient. It would be more efficient if we knew how much of that was working toward this component. That's what's really sliding it. If I would, let's say that was a rope there and I was pulling on a rope, it would be more efficient if I could comfortably do it to get down to this level here and pull it straight out at 45. It would go much quicker, but some of this 45 is being exerted in an upward force. So let's see how that splits out. Now, it's nice that this is a 30-degree angle, but without that, we could still SOHCAHTOA this. If it was a 26-degree angle, we could find this y component with sines. But since it's a 30, I'm going to take advantage of that. The short side of a 30, 60, 90 is half the hypotenuse. This is 45 on 2. That's not really the side I'm interested in. I'm really interested in this. But the middle side of a 30, 60, 90 is the short side, 45 on 2 times root 3. Okay? That is the force that if I was really just pulling this direction is being applied to the table. The 45 on 2 upward force is just kind of a wasted force in this problem. But maybe that's how it's comfortable to pull it at that angle. All right, and work equals force times distance, and we're dragging this thing for 20 feet. So our work equals the force that's really going into this, 45 on 2 root 3 times the distance, 20. And if you go ahead and work that out, that would be approximately 779.42, and that is measured in feet pounds. That's what we talk about when we talk about work. So that is laid out. Everything that's on your test, other than the law of sines, law of cosine problems, where you would have a couple of those. This is not, I've mentioned this to my classes, to those who are here, this is not really a test that's going to necessarily identify the students that are great in this course. This is going to identify the students who have greatly prepared for this test. No surprises, no curveballs, a couple new formulas that you need to commit to learning, and some process. This is a test that may push your time limit within the class if you are not prepared. You've been exposed to everything, but you should know exactly what the next problem brings. This is a test that is more like a music recital. You don't just sort of learn the song and go to the recital and hope it works out. You have that song down pat. You get there, there should be almost no thinking involved on this. This should be entirely mechanical. This goes back to a quote. As I say good luck here, Lucius Seneca, which is oftentimes just referred to Seneca, there's actually a town in Illinois named Seneca who lived back in the time of Christ, said clear back then, luck is what happens when preparation meets opportunity. Well, you got a whale of an opportunity for this test. We're going to find out how you prepared for it.